So in our ninth learning unit, we move on to chapter 21, which is electrochemistry. So we're going to split this learning unit into 4 lectures that we'll talk about. And the first concept that we're going to deal with in today's lecture is how to balance redox reactions. So we'll have to do a little bit of a review with what it means to be doing oxidation and reduction chemistries. And then a main skill to practice is, again, just learning how to balance redox reactions. And we'll learn how to do it in both acidic and basic solution. So a lot of the same principles that we've talked about before for balancing equations will apply here, but something that's new is thinking about, well, the acidity or basicity of the solution is going to affect how we balance a redox equation. A couple of homework problems that allow you to practice this skill. So again, as we culminate in this chapter, we only have one more chapter left in Gen Chem 2, and that actually is to introduce you to organic chemistry. So really the past several chapters have all been kind of leading up to this summative kind of chapter on electrochemistry. We learned about how fast chemical reactions occur in chapter 16. We learned about equilibrium over 3 chapters. And we learned about energy and, again, its correlation with equilibrium in chapter 20. And now in chapter 21, we deal with a specific kind of chemistry as electrochemistry. And so this is really a major field in applied thermodynamics. And so, again, we're going to see how we connect to our last chapter here. And so really what we're seeing a connection with is chemical changes and then electrical work. So at the very end, we're going to have an equation that we'll use that will allow us to sort of relate concepts from chapter 20 with material from chapter 21. So a few slides here just to kind of review some earlier concepts. So you'll notice that these are chapter 4 slides from Gen Chem 1. And so when we learned about oxidation and reduction chemistry, right, we may have learned a couple of different ways to think about this, but this is an important thing that you need to make sure that you remember, that if something loses electrons, it's oxidized, or gains electrons, it's reduced. So you may have remembered Leo the Lion says grr, or maybe you were from an oil rig camp. Oxidation refers to the loss of electrons. So oxidation is loss or reduction is gain. And so really this should be a red eye there. Oxidation is loss, oil, reduction is gain, rig there. So however you want to remember it, we need to remember that when we lose electrons, something is oxidized, and when we gain electrons, something is reduced. And these processes don't occur kind of without being coupled. That is, we call these redox processes because we're going to couple oxidation and reduction reactions. So essentially, somebody is going to be giving up electrons, and somebody is going to be taking them on. So again, somebody who has the least attraction for the electrons is willing to give them up, and they're going to give them up to somebody who has a greater attraction for electrons. So this is just a slide from chapter 21 that kind of summarizes a lot of that same information. Again, oxidation here is going to be something that loses electrons. Remember those reducing agents and oxidizing agents terms. If something is oxidized, it means it's an agent of reduction. It forces someone else to gain those electrons that it's giving up. We learned too about oxidation numbers. So again, if you are losing electrons, that is allowing you to become more positive. So we're going to see an increase in oxidation number. So hopefully you remember from Gen Chem 1 concepts of oxidation number. So anything that's in its elemental or pure state has an oxidation number of 0. And so when zinc becomes a zinc cation here, the oxidation number becomes +2. And I know this can be a little bit confusing because you're thinking, well, wait a minute, I lost something. So how can I become positive? But remember, when you're losing negative things like electrons, you actually become positively charged. The opposite is true when we're talking about reduction chemistry. So again, reduction means gaining of electrons. If something is reduced, it's an agent of oxidizing, so it forces somebody else to lose their electrons so it can gain them. And we see decrease as an oxidation number because we're gaining something negative. So just looking at this very simple chemistry here, if you were to put a piece of zinc metal into any kind of acid, you'd actually see bubbles from hydrogen gas that's forming, and the metal would disappear, and that's because you're converting that solid metal into its cation. And so again, we would here say that the zinc is oxidized and the hydrogen, the protons are reduced to elemental hydrogen. So hopefully that's a good review of concepts that we discussed in chapter 4 in Gen Chem 1. So again, this is another slide from chapter 4, kind of giving us some general rules for how we assign oxidation numbers. If anything, again, is in its elemental form, it has an oxidation number of 0. For things that are ions, we basically take the charge on the ion to be the, if it's a monoatomic ion, we take the charge to be the oxidation number. But again, if we've got polyatomic ions, we need to do some summation of things. And there are some rules here. And again, our periodic table is going to be our best cheat sheet here for being able to figure out what kind of charges we may have for oxidation numbers. So, still important for us to think about oxidation numbers, but remember we balanced chemical equations in chapter 4 last year using oxidation numbers. We're going to teach you in this learning unit a different way to balance redox equations. So this is called the half reaction method of balancing, and what we're going to basically do is we're going to divide a redox reaction into 2 half reactions. The oxidation half reaction, where somebody's losing electrons, and the reduction half reaction, where someone is gaining electrons. And why we do this is in this chapter where we learn about electrochemistry, we're actually going to be talking about electrochemical cells. And when we talk about electrochemical cells in our next lecture, we're actually going to be talking about the energy that we can gain when we physically separate these processes. And so that's how batteries, for example, are made. So this method does not require the assignment of oxidation numbers. So I wanted to review that, not only because it's an important concept that you've discussed before and will be important for our cumulative final exam, but it is something that we will be able to relate to. But again, we're not going to be using oxidation numbers to balance our chemical equations here, our redox reactions. Again, this half reaction method is going to be easier to apply when we know we've got either acidic or basic solutions. We actually need to use this method if we know we've got acidic or basic solutions. Okay, so I'm going to run through the steps kind of very briefly here. We're going to revisit them as we go through a problem together, and then we're going to have one problem I'll ask you to work through on your own. And again, throughout the video here, we'll kind of reveal it in stages as you try to work through it on your own. So again, these steps are provided for you in the chapter summary sheet. So if you wanted to have that kind of handy as you're working through problems. 5 basic steps. We're always going to be using 4 of them, as you'll see on the next slide. The 5th step is only going to be if you're balancing in basic solution. All right, so the first step is we're going to take and we're going to split our chemical reaction into 2 half reactions. So we're going to divide what we call the skeleton reaction. And the skeleton reaction is going to be one where we're going to basically be eliminating any spectator ions. So no spectator ions. So that's what we call our skeleton reaction. Remember, we sort of thought about this when we had net ionic equations last semester in Gen Chem 1 when we sort of did precipitation chemistry. We had our net ionic equation. So again, we're going to divide our basic chemical redox reaction into 2 half reactions. And again, each one's going to contain the oxidized and then the reduced forms of one of the species. And again, we're going to be able to look for non-oxygen and hydrogen atoms to help us find these redox pairs. So again, I'm going to walk through these steps right here. We're going to walk through an example problem together, and then there's going to be one that I'm going to ask you to work on your own. And again, we'll reveal the solution through the video. This is probably the most involved step, and it involves balancing both atoms and charges of the half reaction. So a few steps we need to think about here, so I'm going to kind of highlight them here, and then we'll see it put into practice. The first thing you want to do is balance any non-oxygen and hydrogen atoms, since they're likely to be present only in one species, and as we're going to see in the next steps here, we actually use water and H+ to balance the oxygen and hydrogen atoms. So once you've balanced the non-oxygen and hydrogen atoms, then you go ahead and you balance the oxygen atoms by adding water, and you balance the hydrogen atoms by adding protons. Once we've done all that and all of our atoms are balanced, then we need to make sure we balance the charge. So again, balancing the charge is going to be involving adding electrons, and we're going to add electrons to the side that allows us to create a charge equality on both sides. And one of the things that we'll see is when we have a reduction half reaction, electrons are going to appear on the left side. When we have an oxidation half reaction, they're going to appear on the right. That should make sense, right? Because reduction means we're going to be gaining electrons, so they're going to be reactants. Oxidation means we're losing electrons, so they're going to be on the right side as products. Third step, we might need to multiply or scale up one or both of the half reactions by some whole number integer so that the number of electrons that are gained in our reduction half reaction equals the number of electrons that are lost in our oxidation half reaction. Once we've got all of that stuff balanced, then we add these two reactions together, include the states of matter, and we'll have our final equation. Now the last piece here, and this is sort of a step 5, is if the problem asks you to balance it in basic solution, you basically add the same number of hydroxide ions as there are H+ ions, but you have to make sure to add them to both sides of your half reactions or to your combined reaction. And again, that'll allow you to create water molecules that might be able to be canceled out. This will make more sense as we go through an example. But you only have to do this if the problem tells you that you need to balance your solution or your chemical redox reaction in basic solution. All right, so let's go through one example together, and then I'm going to have you work through and try one example on your own. Again, working through and playing and pausing the video as you need to kind of work through the solution. So again, this is our skeleton equation. You notice that we've got a polyatomic anion here. It was probably maybe from sodium or potassium chromate. And then again, we've got iodide here. Again, maybe from potassium or sodium iodide. But those potassium and sodium ions are spectator ions. So we don't have them here in what we refer to as our skeleton equation. So the first step, remember, is to take that skeleton equation and break it apart into two half reactions. So again, look for things that are related by the elements that are not oxygen and hydrogen to sort of split things apart. So hopefully we see that there's a chromium here and here. So these two belong together as a half reaction. Iodine and iodide. So iodide and iodine here, those are going to belong together as half reactions. So again, the first thing that we do is just identify redox pairs that we're going to have here, and we set them up to be related in two redox half reactions. Okay? Next step, again, this is likely the most involved, so we're going to go through this a little bit more slowly to make sure that we can see how we balance everything here. So when we're looking at this second step, balancing atoms and charges in our half reaction, remember the first thing is we're going to try to balance atoms other than oxygen and hydrogen, since they're likely to be present only in one species. So let's take this guy on the right here. It's a little bit simpler because all we really have is the atom iodine here. So again, we've got I2 over here in elemental iodine, and we've got only one iodide over here. We need to add a 2 in order to balance this. So this one was pretty straightforward in terms of balancing the atoms. Let's take our chromium here. So again, we've got dichromate and then a chromium 3+ cation here. So let's go ahead and balance the chromiums first. We know we're going to need to add a 2 there to make sure that we've balanced those chromiums. Now we have to balance oxygens and hydrogens. So start first by balancing oxygen atoms by adding water. If I've got 7 oxygens that are over here, I'm going to add 7 waters over here. So balance first with water to balance your oxygens, and then balance any hydrogens with H+. Well, by adding 7 waters over here, I added 14 hydrogen atoms. So I need to add 14 H+ over to this side. Okay, so to recap what we did here, and again, this is the most involved and kind of time-consuming step. Balance atoms first that are non-oxygen and hydrogen atoms. Then go ahead, balance oxygen first by adding water, and then balance hydrogen by adding H+. The next step that we need to do is make sure to balance charge. This is a common place where students can make mistakes because if your coefficients aren't right, your charges aren't going to be right. So let's start on the right side here. On the right side, anything that's in its elemental form is not going to have any charge. So the net charge of everything on the right side here is going to be 0. We've got 2 monoatomic anions, so 2 things that have a -1 charge. So the net charge of everything on our left side is -2. If we want to balance this, I've got -2 on the left, I've got 0 on the right. I need to add 2 negative things on my right to get those charges to balance. So that means this is going to be my oxidation reaction because I'm putting electrons on the right side of the equation. Once I rewrite my oxidation half reaction here, it's going to be 2I- goes to I2 plus 2 electrons. That one was pretty straightforward, not a lot to it. Let's go over to this guy on the left here where we have a lot more to consider. All right, looking at my right side, water contributes no charge, and I've got 2 metal cations that have a +3 charge. So the net of charge on the right side is +6. If we look over on the left here, I've got one thing that's -2 charge, and I've got 14 things that are +1 charge. So the net of +14 and -2 is going to be +12. So the net charge on the left side is +12. If I want to have these charges balanced, that means I need to add 6 negative things, 6 electrons to the left side there. Okay? As I pull all of this together and sum everything up, again, I'm going to see that I'm going to have electrons on the left side, which means this is my reduction reaction. If you're ever going through these steps and you see that you're trying to add electrons to the same sides, either making 2 oxidation or 2 reduction reactions, that's a clue that something's not right. Go back and check either your balancing of atoms, your determination of charge, something's a little bit off. But as we add all of this up here, again, I'm going to have 14H plus 1 dichromate anion plus 6 electrons in my reduction reaction makes 2 chromium 3 plus and then 7 waters. Okay, so that was step 2. Again, that's the most involved step probably, but also the most prone to kind of having silly little mistakes that can make your math be off. All right, so the third step then is to think about multiplying one or both half reactions by an integer if necessary so that the number of electrons that are gained in my reduction reaction equals the number that are lost in my oxidation half reaction. So in this case, I have to scale this guy up by 3 so that I've got 6 electrons that are being lost in my oxidation reaction equal to 6 electrons that need to be gained in my reduction half reaction. So not a lot really involved in this step other than kind of checking and making sure that I've got a balance between the number of electrons lost and the number of electrons gained. All right, fourth step really just means we're going to add both of these together, crossing off things that appear on both sides, and then allowing us to put back in specific phases or states of matter. So again, electrons by necessity should cancel here. I'm going to have 6 electrons in my reduction reaction, 6 electrons in my oxidation reaction. Right now, I can see that I've got nothing on either of these sides that are present that I'm going to allow to cancel. For example, if I had had some water on the left side of this reaction and then water on the right side of this reaction, I could have the net sum of those be something different than what was present on both sides. So not something we need to think about here. Truly, the only thing that cancels out here is my electrons. So everything that was present on the left side becomes reactants. So I've got my 14H plus, my dichromate, my 6 iodides. Everything that was on the right side here, I should actually point to here, on the right side here, comes down on the right side of my equation here. So 2 chromium, 7 waters, and then my 3 iodine. I'm going to bring down my states of matter here, whether it's aqueous, liquid, or solid. And at this point, I have balanced this redox reaction in acidic solution. All right, so the last piece was, and this is only necessary if it's asking, is to balance it in basic solution. So if they asked us to balance in basic solution, we're basically going to be adding the same number of hydroxide ions as there are H plus ions. Okay, so what that means is I'm going to add 14 OH minuses to this side because I want them to cancel out and neutralize the 14 H pluses that I have. Okay, but I don't want to undo all of that beautiful work that I did to balance a chemical equation. So in that case, I need to make sure that I put 14 OH minuses on the right. Okay, so now let's see what happens here. When I have 14 H pluses and 14 OH minuses, does that make sense to everybody that that generates 14 waters? Well, I have to remember that I had 7 waters that were on my right. So 14 on my left, 7 on my right is a net of 7 on my left. Okay, so after all of that and after all the dust settles from that, I'm going to have a net of 7 waters on my left. And then this 14 hydroxides, those stick around. So 14 hydroxides on the right. So one of the things that you'll notice is the only thing that really changes, I don't change the number of atoms, the number that I have here, because it's still balanced. But what changed is whether I had protons being around, meaning I was in acidic solution, or I've got OH minus being around, meaning that I'm in basic solution. Remember, this is only a step you'll have to do if you're asked to balance the redox equation in basic solution. If there's not any information about balancing in basic solution, this is the final answer for your redox reaction. Okay, time for you guys to work through one on your own. So here's what that problem is. So here's the balance, or the skeleton, I shouldn't say it's not balance. Here's our skeleton reaction here for permanganate anion reacting with oxalate anion to generate manganese dioxide and carbonate anion. So one of the things I want to make sure to highlight for you guys is, because we're bringing back a lot of polyatomic ions, make sure you're doing your work not only to practice for the final exam, but it's important for this chapter of making sure that you're good with naming species, because you are going to see problems that have you have to think about just chemical names rather than looking at a chemical formula. Notice that this one does ask us to balance in basic solution. All right, so what I'm going to do, and again, I'm sure you could have this sheets in front of you to walk through the different steps. I'm going to tell you what the step is, and then I'm going to ask you to pause the video and try to work through it on your own. Okay, step 1 is to take our skeleton reaction and divide it into 2 half reactions. Again, looking for things that are related by non-oxygen or hydrogen atoms to find these redox pairs that will create an oxidation and a reduction half reaction. So go ahead and pause and try to figure that out for this problem. All right, hopefully we see that the manganese should go together. So our permanganate anion, and then our manganese dioxide, and then our carbon and oxygen here, specifically our carbon here. So we've got carbon with oxalate and then carbon with carbonate. So first step is pretty simple, just taking and dividing out, and again, we don't need to think about phases or anything at this point, but separating our skeleton equation into a reduction and an oxidation half reaction. And at this point, we don't necessarily know which is which. All right, moving on for the next step. This is going to be the most involved because it has to do with balancing atoms and charges. So remember, first go through and balance atoms other than oxygen and hydrogen, then balance oxygen by adding water, balance hydrogen by adding H+, and then balance charge by adding electrons. So go ahead and pause the video and see if you can figure that out for both of these half reactions. All right, so what I've got shown here in red is what we'd use to balance the oxygen and hydrogen atoms, okay? For this guy, I had already written it right here. There was a 2 that was there. That actually shouldn't have been there because it wasn't part of what we had here. But we're going to have a 2 that gets added here to balance our carbon atoms. And then we didn't have to do anything to balance the manganese here. But when we think about balancing the oxygens, we need to add 2 waters to account for the 2 oxygens that are over here. And then again, we've got 4 oxygens that are over there. I should have said we've got 4 oxygens over here, 2 that are here, so we need to add 2 waters to finish balancing those oxygens. And because we added 4 H pluses that we have over here, now we're going to add 4 to our left side here. Coming over with our oxalate and our carbonate here, we could look and see that we've got 6 oxygens that we have here, 4 already on this side, so we're going to need to add 2 waters. Adding 2 waters means adding 4 H+. Go through now and balance our charges. Again, nothing is charged over on our product side here, so the net of everything over there is 0. We've got 4 positive 1 things and 1 minus 1 thing, so that ends up being a net of -3. To have it equal a net charge of 0, we're going to have 3 electrons on our left, so this guy is our reduction half reaction. Looking over here on the right, we're going to have, again, no charge contribution from water. 1 oxalate anion contributes a -2 charge. And even though we've got 2 carbonates at -2, we've got 4 H+ at +1. So the net of everything on this side is 0 as well. Note over here it was 0 because everything was neutral. Over here it just happens that they cancel out. So to have -2 equals 0, that means we need to have 2 electrons on the right side. All right, remember step 3 is going to be looking at these half reactions. So again, 4H+, MnO4- plus 3 electrons. This reduction half reaction has 3 electrons. This oxidation half reaction only gives up 2. So we're going to need to do some scaling here so that what's given up in our oxidation reaction is equal to what's taken on in our reduction half reaction. So go ahead and pause the video and see if you can figure out how to scale these reactions up. All right, hopefully you see here that this is one where we actually have to scale both of them because the common factor is going to be 6 electrons. So we're going to multiply each of these by a factor that allows us to get to 6 electrons. So again, our reduction half reaction, which we have shown right here, okay, when we took and we summed up all of this, we need to scale this up by 2. We need to take this guy, which was our oxidation half reaction, and we need to scale that up by 3. I'm going to have that on the next slide. And remember, the next slide, our last step in balancing an acidic solution, is just basically to add together our balanced half reactions and include states of matter. So one of the things to take note and to think about here is in this particular example, we have one half reaction that has water as a product and another half reaction that has water as a reactant. Same thing with H+ appearing on both sides. So remember, we want to have the net of water and H+. So think about what those nets might be. See if you can figure out what the overall summed and now balanced redox equation is here. All right, so again, a lot that we have here. If we're looking at 8 H+, and again, we're kind of scaling up this guy where I'm doing summing and kind of scaling at the same time. So 8 H+, 2 MnO4s, and again, we've got then 6 waters and then 3 oxalates. That's how we get all of our reactants here. All of our products are going to be 2 MnO2s, 4 waters, 6 carbonates, and then 12 H+. But remember, we already noticed that there's going to be water on both sides and H+ on both sides. So what I've done now is said, you know what, if I had 6 on the left and 4 on the right, the net is going to be only 2 on the left. Same thing with H+, 8 on the left, 12 on the right means there's a net of 4 on the right. So summing and putting all of that together here is our balanced redox reaction in acidic solution. Just as a good sort of practice, one of the things that you can make sure to do is go back through, count all of your atoms. Everything should balance in that regard. All right, the last piece is to say, oh, this asked us to do it in basic solution. Remember the steps and the directions for balancing in basic solution are we have to find out where the H+ are, and we're going to add the same number of OH- ions to both sides of our half reaction. That, again, allows us to make sure that it stays balanced. When we add H+ and OH-, that's going to generate water. And then again, we'll have to reconcile where we have a net accumulation of water. So go ahead and pause the video and try to finish out this problem in basic solution. All right, we had H pluses that were on the right side of our equation here when we were in acidic solution. So we had 4 OHs that we needed to add in order to neutralize that. We have to make sure to add 4 OH minuses to the left as well. When we add 4 OH minuses to the side that has 4 H pluses, that generates 4 waters. Remember, we had 2 that were on the left. So 2 on the left, 4 on the right is going to net us 2 on the right. So now rewriting everything, accounting for the fact that we've added 4 OH minuses to the left, and we have net now of 2 waters on the right, we get this final balanced chemical equation, balanced now in basic solution. So conceptually, not really super difficult here, but it's just one of those things that we just got to make sure we keep track of all of our steps and all of our species along the way so we get to the final correct balanced chemical equation.